Hello, my name is Rob Reynolds. Welcome to College Algebra, Chapter 12.1. We're going to learn how to do systems of equations, substitution, and I'll even show you how to solve systems on a graphing calculator. So, systems of equations oftentimes come up in word problems where you have different situations and you want to find solutions for both systems. We have different types of methods for solving systems of equations. One is the elimination method, or linear combinations, where you're actually trying to eliminate either the x's or the y's, oftentimes by multiplying through by a common factor. We also have the substitution method. If one variable is by itself, it's easy to solve for that variable and then substitute that in to the other equation. Sometimes we're going to look at, or within this video, we're going to look at solving systems containing 3 variables. We'll probably use our calculator for that. If I have 3 variables and only 2 systems, we'll have infinitely many solutions. I'll do an explanation of that as well. But most often we will see a consistent, independent solution, and we're going to start with the graphing method. And that just means there's one solution and there will be a point of intersection. If the 2 lines are parallel, we call that inconsistent and there's no solution. And consistent dependent means there's infinitely many solutions where basically the 2 systems are equivalent to each other, and if you were to graph them, one line would fall on top of the other line. So the graphing method, pretty easy, different ways how to graph. This is in slope-intercept form, so I'd start at the 3. The y-intercept, I would do the slope, rise 4, and run 1, and I would continue doing the slope over and over again to fill up the graph. Instead of rising 4 and running 1, we could go down 4 and 1 to the left. And what this does, if I fill up the graph, one of these green dots will hopefully be the intersect for my second line. So if I carefully try to draw that line in, I'll start here at -2, do its slope. If this is in the form y is equal to mx plus b, the slope would be -1/1. There's your rise, there's your run. So I'm going down 1 over 1, but instead of going down and to the right, I could go up and to the left, and there's that point of intersection that I was looking for. We would name it -1, 1. If the systems are not in slope-intercept form and they're in standard form, the easiest way to graph this is x and y intercepts. I'll put an x in for the 0 for the top equation, and I'll look at the equation -y equals 1, which means I need to divide through by -1, so y is -1. And if I put a 0 in for y up here, that just looks like 2x equals 1. That's not a very nice point. If I divide by a half, it's hard to plot 1/2, 0. So there's a definition. If I give you an equation in ax plus by equals c form, which is standard form, the slope is defined as -a over b. So basically it's the opposite of the a term divided by the b term. In this case, the slope would be the opposite of 2 over the -1, or basically 2. So I'm going to plot the one good point that I have, which is 0, -1, and then do my rise over run. Rise over run. Rise over run, and fill up the graph. Instead of going up and to the right, you could go down and to the left. And again, I keep filling up the graph until it's full of dots. Let's try for this green line, x and y intercepts, just like I did before. If I let x be 0, divide through by a -2, I get -1. If I let y be 0, divide through by 4, I get that 1/2 again, which I'm not crazy about. So I'll do my -a over b definition again, because it's in standard form. The opposite of the first number divided by the second number, and I get still a slope of 2. And look at that, 0, -1, slope of 2. It's the exact same line, so I would say infinitely many for the solution. This problem looks like a mixture of both slope-intercept and standard form. For the slope-intercept, it's in the form y equals mx plus b. Here's my y-intercept of 1. The slope is rise 1, run 1. And the second line is in standard form, and so I'll graph it using x and y intercepts. If x is 0, y is, if I divide through by -2, -4. And if I let y be 0, divide through by 2, I'll get a 4. So I'll plot the point 0, -4, and 4, 0. And they appear to be parallel, but I'm going to go back and try to define this slope and actually just check the slopes by using -a over b and get a slope of 1 here. And sure enough, this slope was also 1. So now I'm convinced that there would be no solution to this problem. Solving equations using the substitution method is useful if there's no coefficient in front of a variable. Here's a -1 in front of the variable y, and it's easy to solve for, so I'll spend just a little bit of time solving for y by subtracting off 4x, giving us y is equal to 4x minus 3. Since I solved for y in the denominator, I'll plug it into the numerator and rewrite the equation. 2x plus 3 times the quantity of my new value of y, which is 4x minus 3. Solving for x, I'll end up with 14. X is equal to, adding 9 to both sides, this reduces to 4/7. You can see this method is a little bit more accurate. I would have never been able to find 4/7 using the graphing method. To find the x, I'm going to plug, to find the y, I'll plug the x in. I can go to the top equation or the bottom equation and solve for y. Let's see, this is 8/7, and I'll make this 7/7 just so that I can subtract off 8/7 from both sides, giving me 3y is equal to -15/7. And then if I multiply both sides by 1/3 and cancel, I'll get y is equal to, let's see, this is -5/7. Now, I'm not a big fan of these answers. I don't know if I made a mistake or not, so I'm going to check this on the graphing calculator. So pulling up my calculator, I'll go to my matrix function, second matrix. I'm going to edit the matrix as 2 rows by 3 columns. I've got row 1 here in blue, row 2 here in pink, and then 3 columns, 1, 2, 3. So I'll call this a 2 by 3 matrix, and I'll edit the matrix using the coefficients and the answers. So 4, -1 for that bottom row, and 3. I'll hit second matrix again, go to mathematics, and reduce row echelon. If you arrow up to B, oops, I gotta quit, I'm so sorry. So let's try that again. Second matrix, let's go to math, arrow up to RREF. Calculator's responding a little bit slowly. Then I'll hit second matrix for the 3rd time and press enter, and I get an answer like this. Doesn't look very nice because it's in decimal form, so I'll hit math, enter, enter, which will convert it to a nice fraction. And sure enough, that matches my answers, 4/7 and -5/7. I'll show you that process again here in just a little bit. But to make sure that you understand the substitution method, I would either solve for this top y here, I'd probably solve for this top x, solve for the top y here, probably solve for the bottom y. Getting y by itself, -4x plus 8/3. If you solve for the bottom, plug that into the top. If you solve for the top, up here, x is equal to y plus 5, then you plug it into the bottom equation. So that's substitution method. The elimination method multiplies through by a common coefficient. So if you want to eliminate the x's, you'd have to multiply both sides here by 2. You could also choose to eliminate the y's. Sometimes it's easier to multiply through by, or eliminate the x's. In this case, I think it's pretty easy to eliminate the y, so I'm going to choose to multiply through by 3. Because in the second equation, that'll give me a negative 3y, where in the top equation I had a positive 3y. And if I add, those will eliminate, or cancel. And again, it looks like I'm going to get some fractions here. 8/14 reduces to that 4/7 answer again. And then I would take that answer and plug it in, either to the top or the bottom, it does not matter, and solve. In this word problem, we have tickets being sold generally for $8. We'll let that be X because I don't know how many the tickets are sold. But senior citizens get a discount, looks like a $2 discount, so they don't pay $8, they only pay $6, and I don't know how many senior citizens, so we'll let that be Y. And the total cost, so we'll call this all of the money equation. The total money gain from this theater is $3,580. Now we also know we don't know how many patrons bought the $8. We don't know how many senior citizens there were and why, but we do know that the x plus y will equal 525. So there's my system, and again I could solve that either through elimination method, through the substitution method. I'll show you one more time on the calculator. Going back to second matrix, editing, again it's a 2×3. The coefficients are 8, 6, and 3580. One, 1, 525. The nice part is since I just did this in my calculator, if I hit second quit, and then second enter is a quick way to recall the RREF, reduced row echelon, and I have a new matrix A, so there's my answers. It says x equals 215, and the y is 310. It's probably the fastest way to solve. So again, the author agrees x is 215 and the y is 310. If we try this calculator method for an inconsistent or dependent system, your calculator will do this just fine. I'll show you what the answers look like again. Another 2×3, 215, 428. I'll hit second quit and do a recall again. And you can see the top equation, actually let's go to the bottom equation, 0, 0, 1. That's a false statement. 0x plus 0y equals 1. That means 0 equals 1, so that's false. So your calculator is telling you there's no solution. It's an inconsistent, that's a false statement. No solution. If you were to graph them, the lines would be parallel. If it's a true statement, I'll edit 2, 1, and 4. Let's try that again. Quit. Second enter is a recall. And now you can see the bottom equation is a true statement, 0, 0, 0. So that means there's infinitely many solutions. If there's infinitely many solutions, don't leave your answers infinitely many. Let's write them in terms of a parameter. So let's solve. The top equation is pretty easy to solve for. Y is equal to negative 2x plus 4. So I would say letting x be the parameter, we could say x is the solution, but then instead of sticking a y here, I'll put it in terms of x. Negative 2x plus 4 would be the y answer. So this is called a dependent solution. And there's the answer. If you have systems of 3 variables, sometimes there's one solution. Sometimes there's infinitely many solutions because the planes could all cross at the same line, and it is possible to have no solutions if all the planes are parallel. So we do the exact same thing. I'll go back to my matrix. I'll edit it. However, this time I've got row 1, row 2, row 3, column 1, column 2, column 3, and column 4. So I'm going to call this a 3 by 4 matrix. I'll edit this. I'm going to quit. Again, just to remind you, if I hit second matrix, go to math, I can arrow up to reduce row echelon, that's letter B, and then second matrix again, and just recall matrix A. If I get decimals, I'll hit math, enter to clean those up to get nice fractions. Ooh, I wouldn't have wanted to do this problem by hand. That looks like a pretty bad solution. And we'll see if it matches. The book wants you to go through and solve this. I wonder if I made a mistake somewhere. Typing something in, checking my matrix A really quick. Let's see an error. I disagree a little bit with the solution, so again, we'll see if we get an inconsistent solution. We can write it in terms of a parameter. I'll try this one more time. Still a 3 by 4. All right, the bottom row says 0, 0, 0 equals 1, and that means it's no solution. 0x plus 0y plus 0z cannot equal 1 because 0 never equals 1. It's a false statement, so there's no solution. You could have gotten that as well by and then for the dependent, we need to write this in terms of, usually we let z be the parameter. I'll do a recall since I already have up. The bottom row says it's 0, 0, 0, 0. So that means there's infinitely many solutions. To write this in parameters form, I'll do a little solving. Looks like from the first two rows it's really easy to eliminate the y's if I just add them. So 3x plus 3z is equal to 3, and that means x plus z equals 1, and therefore x is 1 minus z. I'll go back and eliminate the x's so I can solve for my y's. To eliminate the x, I'm going to multiply the top equation through by, the second equation through by negative 2. So negative 4x plus 2y minus 2z is equal to negative 4. I'll just keep the third equation the same, and I'll add 3y, 3z is equal to 0. This means that if I divide through by 3, y plus z is equal to 0. And then solving for y, I'll just get negative z. So remember, this is in terms of x, this is my y, this is my z, but I'm not going to write the y. I'll put everything in terms of z, letting z be the parameters. My calculator told me the same answer. If you notice, that top row says 1x, 1, it says 1, 0, 1, 1. So that's 1x, 1z equals 1. And that's equivalent to this. And then the second row says 0, 1, 1, 0. And 0, 1, 1, 0 means no x's. 1y, 1z is equal to 0, which is equivalent to this. It still gives me y is equal to negative z. So if you wanted to, you could just pick off those equations from your calculator. Please check out Blackboard, where I have all of the notes for all of the examples. If they ask you to find a quadratic function, the book is going to teach it by ax squared plus bx plus c is equal to y. And they're going to ask you to plug in the x's and the y's and start writing systems. But I wouldn't do that. I would go to your calculator and do what we were doing before. By under stats, you can edit the list. If there's previous numbers in there, you can clear out the lists. And I'll put x's under list 1. Looks like negative 1, 1, and 3. For the y's, I have negative 4, 6, and 0. And I'll just ask my calculator to calculate. Under statistics, if you go to calculate, I can find the quadratic regression under number 5, and I can just calculate the equation. It gives me the values of a, negative 2, b is 3, b is 5, and c is 3. So negative 2, 5, 3, which is the same thing as saying negative 2x squared plus 5x plus 3. You can graph that equation and see if that's true, but the author gets the same thing. If you have questions, feel free to email me. Thank you.